Okay, so welcome to the third video in the implementation module for Software Engineering 1, and today what we're going to be talking about is integration. So the last time, in the last video, what we did is we talked about code smells, and we talked about kind of best practices around actually physically writing code. So we talked about coding practices in terms of naming your identifiers correctly, how to use comments, things like that. And today what we're going to do is we're going to talk about how you can take all of those pieces of code that you have written using those guidelines and stick them all together through integration and actually create your system. So all the kind of implementation stuff that we've talked about up to this point has really been about building the puzzle pieces themselves. And then this last video is really about taking all those puzzle pieces and actually building the puzzle out of it. So as we talked about in really starting in the design videos, what you really want to do in design is break everything into as many subsystems as possible so that you can have subsystem teams working in parallel. So if you can split your project up into 10 modules or 10 subsystems, you can have 10 groups of people working in parallel, and at the end of that work effort, you're done. You don't necessarily have to have 10 individual units built in series. So the problem is that you ultimately have to integrate those 10 subsystems together, or you don't really have a product. You don't have something that's often very marketable. So integration turns out to be one of the harder aspects of software engineering, because what you're trying to do is you're trying to take these 10 pieces of software that were really kind of built in a lot of ways in a silo, and then stitch them together in order to actually create the end product. So if you think about kind of a naive approach of how to do this, we could call that something like implement and then integrate. So what this would be is like building your 10 modules or your 10 subsystems, and then after all of that development is done, then you would try to stitch them together after development is done and tested. This is not such a great idea because what you ultimately end up with is a bunch of squares in the sort of tile floor that you're trying to lay. And if you've ever laid tile, not all of the tiles are going to be perfectly square, and the less conversations or communications you have between your subsystem teams, the more those pieces of software won't actually line up correctly together. And so what you end up with is a situation where you have to go back potentially into 2 or 3 or 4 or 5 of these subsystems and start making changes that could then ripple to other subsystems in order to actually line them up correctly. So what we want to do is we want to come up with this integration strategy that allows us to perform parallel work, but then also integrate as early as possible so that we understand the actual shape that these subsystems need to take in order to be stitched together into the correct final product. So if you think of a kind of academic exercise, so where you're trying to build a software system or platform that has something like 20 modules, and you want to use something like implement and then integrate, you're going to build each of those modules, potentially 20 different teams are going to build one module a piece, and you're going to test each of those modules. And then after you're happy with the test results of each of those modules, then you're going to stitch those modules together, and then you're going to test the entire project from kind of end to end. And so the worst case scenario is you find something kind of horrible between 2 modules that then ripples all the way out to the rest of the modules. And so it could be that the bug itself actually ripples out and has lasting effects on the rest of the modules, or it could be that the bug fix, so the correction that you need to make to the software, then has to be adopted by those 17 other pieces. And if you had found this earlier, instead of building the 17 other modules in an incorrect way and then correcting it, you would have been able to build those in the correct way from the very beginning. And so there's also this kind of gray area where if you wanted to do implement and then integrate, you would have to understand a little bit about how those components themselves have to stack up with one another in order to really build out the system. Most of the time, these subsystems have clear interaction points. So if you're trying to build the printing component of an operating system, you're going to understand that there is some interface at the very beginning where data is passed to your module for printing. So you're going to have to understand something about the interfaces between these modules in order to actually do your work. Most of the time, how this is handled is the teams, so the 20 teams, the 10 teams, or whatever, will agree upon these interfaces. So not necessarily software interfaces, and in some cases they are software interfaces, but the method calls from one module into another module. And what they do is they build sort of stub methods that are fake. They generate fake data, or they take in data and don't actually do anything with it. And they allow you to simulate or mock calls across the subsystem interface. So you can make a fake call to the printing system, or you can take fake data from outside of the printing system and actually test your module in its entirety. And in general, if you're going to use a kind of implement and integrate approach, this is entirely reasonable. And actually, this helps you a lot with things like unit testing because you're forced to mock all of the interactions of your system with all of the extra system things. So not only are you going to be able to perform unit testing for your specific units using whatever integration you want, or mock integration you want, but you're also going to be able to build integration tests with these mock interfaces, and you're not going to have to actually go across team to do that. Each team can have their own mocks. The problem is if you spend a ton of time building a mocking infrastructure, and if you spend a lot of time on the actual stubs themselves, what you're actually doing is kind of throwing money and time away. Because if you are building mock code, that mock code is obviously going to be thrown away and then replaced with the actual code you're integrating with whenever integration actually occurs. So this is, again, kind of a continuum of experience, right? What you want to do is you want to have enough mock integration happening that you can be fairly confident that when you perform actual integration, you're protected from risk. But you don't necessarily want such a complicated or rigorous integration testing or mock situation that you're spending inordinate amounts of time trying to build and then maintain that code. So what you want to do is you want to perform integration as quickly and as fluidly in the development process as possible. And you want to do that in such a way where if you fail, you're going to fail very quickly and very catastrophically. And this is often called a sort of fail fast approach. What this means is that it's not what it means. What I'm trying to say is that it's very bad if you fail and you don't recognize it. So you want to be very aware that you failed, which is why you want it to be catastrophic. And you don't want to spend a lot of time on an implementation that is ultimately going to fail. So if you are going to fail, you want to waste as little time as possible on code that's ultimately going to have to be refactored. So what you want is you want to be able to perform integration testing throughout the kind of life cycle of the development. And in doing the integration testing, what you're actually doing is performing integration of the systems, and then as soon as tests fail, you're able to react, and you don't end up with a situation where you're trying to integrate everything at one time and then fix all of the issues at one time. So this can kind of pile up toward the end of a project. So there are two primary kind of ways of doing this, and again, it's kind of a continuum situation. On one end, you have top-down, and on the other end, you have bottom-up integration. And basically, what you can think of is in your system, or in your stack of subsystems, you're going to have some systems that call other systems. And they're going to form some sort of dependency chain. So there's going to be some class that is always calling another class in your system. and there are going to be classes that are only called by other classes in your system. And so top-down and bottom-up integration starts at either end of that dependency chain, and there's obviously going to be pros and cons to either approach. So in order to make that a little bit more rigorous, you can kind of lump all of your artifacts in the system into two groups of artifacts. And if you haven't heard the term software artifact before, a software artifact literally is just a piece of code or a document, a piece of documentation or something like that. And here, what we're talking about is artifacts in terms of classes potentially, or code procedures or something like that. And so you have logical artifacts, and these logical artifacts actually perform all of the decision-making flow. And so logical artifacts are things like service methods that kind of usher data from point to point. And you have operational artifacts that actually perform business logic. And so these would be things that do much more than just CRUD. They're things that perform validation. They're things that actually create new bank accounts or bank transactions based on user interaction, things like that. So what you would often want to do is both bottom up and top down integration at the same time, because you can think about all of the sort of ways that you can mess up the dependency chain if you only go in one direction. So the sort of de facto or best way of performing integration is often called sandwich integration, where you perform bottom-up integration on logical components and then top-down integration on operational artifacts. And what you want to do is you want to perform those pieces of integration separately, and then after you have performed those two pieces of integration, you can kind of integrate those two layers together, and then that amounts to basically just ironing out all the problems in the intersections between your logical and your operational artifacts. The thing that is the most problematic about integration is the interface between the two artifacts. And so interface changes themselves are really, really, really important to think about. And so if you're working on production code that has already been released into the wild, you really want to be careful about making any interface changes at all. And if you're absolutely required to do so, you need to make sure that there's some sort of remediation concept in place to make sure that people who are calling your code are going to be able to continue doing so. And so if you think about what this means kind of concretely, is if you have a method in your class and that method accepts 3 parameters, but you are past 2 parameters, suddenly your method call is not going to work anymore, and potentially it's going to cause a compilation issue, and that's one thing. It's a fail fast situation where somebody's going to be mad at you and then send you an incendiary email that you broke everything. But if you're working on something that has maybe a public-facing API, potentially third-party applications are going to stop responding, and you're not going to know that they're going to stop responding until you get a bug report that your API doesn't work anymore. So interface changes are probably the #1 place where you can see breaking changes in production-level code, and there are tons of ways around it, and there are lots of best practices. But basically every high-level language that you could possibly think about at this point has optional parameters. So if you wanted to do something like add a new parameter or a third parameter, you would maybe want to make that third parameter optional so that anybody that's calling with 2 parameters in a legacy situation would still be supported. Or you would want to provide a method override if you're using an object-oriented design. In that override will allow the new code to work in the new way to support the new feature that has the third parameter, but it would also provide legacy support for calls that predate whatever this brand new feature is. And so you also want to be really sure that you are using what's called sort of hidden code correctly. So it might be that you're trying to use a library method, and the library method's name or its identifier is very expressive, and it's sort of very easy for you to understand the intent and why you might want to use that method. But if you don't have visibility into what the method is actually doing, you can run into situations where you call the method and you get unexpected results. And so my kind of favorite anecdote about this is I was once working on a system that had SSB eventing. And so basically the idea is you have this giant queue of messages, and that message queue has a service that reads and pops the top message off and then performs some business function based on the message, and then comes back and then reads the top message and then does some processing. And that SSB framework had the ability to clear the stack. So there was a dispose method, and the idea was that the dispose method would then pop everything off the stack and then destroy the actual data structure, so that you weren't storing stuff and leaving things hanging around. But what actually happened is that library call was just throwing a not implemented exception inside of an empty try-catch. So what was actually happening is I was calling a method that did absolutely nothing. And so every time the SSB queue was put up and a whole bunch of messages were plopped into it, and the service stopped, you would have this massive stack of messages that didn't actually go anywhere. Nothing actually happened with them. So this is a great example of how you trying to integrate with a third party in a lot of ways can be fraught with a lot of peril. You might not have any control over what's happening inside of that method, but you do need to test to make sure that you're getting expected behavior, because if a situation like that happens in a production environment, you potentially are going to have servers crashing because they run out of memory, or you're going to have a lot of performance issues because you're using resources and never actually freeing them up. So from the perspective of a person writing the API, you need to be very sure that your implementation actually does what the identifier says it's going to do. So if you have a dispose method, it should actually dispose of things. But if you are trying to consume that API method, you need to verify before pushing your code to production that the third-party API is actually doing the things that it's promising to do. So the last thing I want to talk about is something that we're going to spend a lot of time talking about in a couple of weeks, and that is the traceability problem. So in the implementation phase, particularly toward integration, we're trying to put everything together. Engineers usually kind of forget about bookkeeping. They don't necessarily care about keeping up to date with all these requirements documents and all that kind of stuff that we started the semester talking about. And that's unfortunate, because this is actually the part of the project where that bookkeeping exercise is probably the absolute most important. And there are two main aspects to that bookkeeping exercise. And the first one is bug reports, and the second one is feature requests. So what can happen is you as an engineer can see a problem in a piece of code, and by nature you'll want to go in and fix that piece of code without raising a bug, and just sort of fixing it and then checking it in. And I can probably guess with like maybe 85 or 90% accuracy that is a situation that has already happened in your group, and you might be the person who has checked in the code without raising a bug first. So we're going to talk a little bit about why that's not necessarily great. So if you have a situation where you are checking in a piece of code, you should always be able to link that piece of code to either a bug or a feature request. And that seems stupid, but I'm going to tell you why it's not. If you are checking in code and you can't link to a bug or a feature request, what that means is you are adding code to the project without that code being requested. So either you are adding unrequested functionality, or you are covering up a bug that otherwise would educate people on what they're doing incorrectly in the future. So the way that this kind of thing typically happens is if you're new to a project, you'll be given some bugs to fix, and you will immediately kind of go to the code base and try to look through bug requests to see if there's anything similar to the bug you're trying to work on. If you have not raised a bug and you have just fixed the bug in another check-in, you are eliminating the possibility that a new person could actually learn something from that previous mistake that your team made. So that's not necessarily great. The third situation is kind of a more systemic issue, and that's that you could have fundamental failures in either requirements gathering or with design. And if you don't raise a bug and identify those defects, potentially you are covering up whole layers of defect in your process. So not only are you not allowing new members to learn anything from your past mistakes, but you're also covering up the fact that your software organization is not actually as efficient as it probably seems on paper. And this is kind of okay until you onboard a whole bunch of new projects, or the person who's being a rock star behind the scenes and actually fixing a bunch of stuff without raising issues leaves the company. And in that latter situation, you're going to think that overnight, suddenly your software company and your project don't work anymore. And it's really because somebody has been kind of pulling strings behind the scenes and fixing things without raising the fact that they're fixing things that nobody else maybe understands or knows about. So bug reports can come from a variety of different places. They can come from developers, like we were just talking about. If you see an issue in the code and you want to fix that issue, you should definitely raise a bug and then check in your change to resolve that bug. But they can also come from an end user that has never even seen an IDE before. They have no idea what language the thing is written in. They have no idea why they're seeing the error that they're seeing. And it's important that if you pick up a new bug report and you have no clue what that bug report means, like you didn't write it, and the language that's in the bug report itself is from a user, and the user has no idea what the error means, and the user doesn't really even put in reproduction steps for the bug, it's really important that you try to contact that person or contact the part of your company that interacts with that person, so that you can get a sufficient understanding of the situation prior to changing the code or even trying to understand the situation. Because if you spend hours and hours and days trying to reproduce a bug that isn't actually a bug, then you are not helping your software organization be efficient. And if you make changes, potentially you're going to fix some very small use case, but you're going to break a very large use case that a whole lot more people are using. So there are tons of what people refer to as shot-in-the-dark fixes. So these are bugs that are usually not reproducible. They're bugs that happen 3 times a month on one machine in a very remote area of the building or something. And you have kind of an idea of how you could fix it, but there's no way for you to empirically sort of verify that your code change is going to fix it. These things are a notorious source of technical debt. What typically happens is you put in some sort of defensive code, or you put in a try-catch to try to mitigate the issue the next time it happens. And what ends up happening is you never see the bug again, which is totally fine. But that change also covers up a whole bunch of other bugs, so that you have no visibility into actual issues that are happening, and you find out months later that there's a data issue that is caused by your fix, or there are a whole bunch of people that are actually secretly mad about the system because of some minor issue that was raised by the fix that you tried to implement for that other issue that you couldn't reproduce. So there is often a type of bug or a bug state called works on my machine. You'll see this all over the place in GitHub and Jira. Basically what this means is that somebody tried to raise a bug report, and no one that has picked up that bug report can reproduce their issue. And so this is particularly true in open source projects where people are extremely distributed. They're working on 500 different versions of the operating system and 4 different operating systems. They're running on various hardware that's not standardized. And basically what works on my machine means is that someone somewhere has an issue, and that issue is documented in the bug report, but not everyone has that issue. And one of the things we're going to talk about after testing next week is maintenance and how you try to actually triage a lot of these bug reports. So works on my machine indicates that potentially there's only a handful of people that have the issue, and maybe you need a workaround rather than a really huge bug fix or something that would otherwise be a shot in the dark fix. You can't actually reproduce the issue, so you can't empirically verify that your code is going to fix the problem. So at the end of the day, the things that you need to remember are that every time you change anything that isn't a comment or formatting, and you check that change into your repository, you could potentially be breaking stuff. So it is true that the smaller the code base is, the happier everyone is. The users will have a more stable experience. The testers have less testing to do. Engineers have less stuff to maintain. And as you add additional code, if that code is not asked for, if that code just does some stuff that you as an engineer think is cool, but it doesn't actually help the marketability of the software or doesn't actually provide new functionality, ultimately somebody's gonna have to pay the price for that change. So the thing that I want to stress the most is that if you are adding code and you don't understand why you're adding the code, you should take a step back and you should talk to your teammates, you should talk to the project manager, and you should be very, very careful about your check-ins, because if you are just checking in code for the sake of checking in code, you're probably adding to technical debt more than you're adding to the functionality of the system. And so you will start to see this manifest itself near the second iteration of the group project, where everybody is trying to make sure that they have a whole bunch of lines of code checked into GitHub for the grade. But if you're checking in code that's sort of nonsensical, all you're doing is making the project more and more and more unstable, which is not necessarily the situation you want to be in. So that kind of wraps it up for this conversation. So we talked a little bit about integrating all of these pieces together, and we talked about bug reports as a way of trying to mitigate risk as you're building your subsystems, but also as you're trying to put those subsystems all together. And so what we're going to do next week is we're going to talk about testing, which is sort of the last proper part of software development before we go into maintenance and support. But in testing, what we're going to do is we're going to find a way of kind of en masse building these bug reports that then feed back into the implementation section of the development lifecycle, so that we can kind of iteratively refine the software until we ultimately pass all the tests, and then we're ready to go to market. So just some housekeeping things. The first iteration of the project is due next Friday. So you have essentially 7 days to work on that first iteration. One thing that I want to bring up is the fact that you do not have to have a fully functioning piece of software for the first iteration. What you have to do is you have to have a really good plan for how you're going to build the software, and you have to have very clearly delineated functional and non-functional requirements. So even if you don't actually have a single line of code written, it is still possible to get an A for the first iteration. So don't worry if you haven't made it to the implementation phase. Just make very sure that you're doing the first couple of phases of the project very, very well. Next week we'll also have the first midterm, so it's kind of time to start doing some review over the videos, review over the PowerPoint slides. Please send me questions if you have any at all. The test will cover everything up through testing, so instead of having a unit quiz, you will have a test that is cumulative of everything in the class, and it will be exactly like a quiz. I will send out an email that specifically talks about the logistics of the test, but if you have accommodations through the SDRC and you feel that you need accommodations for the exam, please let me know and I am happy to do that. I have a list of people who have sent me SDRC accommodations, but it is always good for you to email me just to make sure that, that I'm aware and that everybody is being taken care of correctly. And with that, that's really all that I have for the week. Thank you very much for tuning in, and I will see you at the meeting tomorrow. Thanks.